WebRTC. Exchange real-time audio-video streams with your friends entirely in the browser.
I'm here live. I'm not a cat.
If you want to build your own video conferencing app to capitalize on the work-from-home boom, then WebRTC is the API you're looking for, because it allows you to establish a peer-to-peer connection between two or more browsers, where they can exchange audio-video media directly, without the need for a third-party server or native app. It works like this. The first peer will create an offer asking for another peer to connect to them. This will result in an SDP object or session description protocol, which contains information describing the peer-to-peer connection, like the video codec, timing, and so on. The data will then be saved in a server, where it can then be read by another peer to answer the call, which is achieved by creating an SDP answer and writing that to the server. This process is known as signaling, and it's handled by a third-party server. The signaling server allows the two parties to securely exchange connection data, but never touches the media that's actually transmitted between the peers. But here's where things get tricky. Most devices in the real world sit behind firewalls, and IP addresses constantly change thanks to network address translation. This makes peer-to-peer connection complicated from a networking standpoint. But luckily, there's a standard called Interactive Connectivity Establishment, or ICE, which helps clients coordinate the discovery of their public-facing IP addresses. Now, both peers will generate a list of ICE candidates, which contain an IP address and port that Peer 1 can use to connect to Peer 2. In the background, WebRTC will do this by making a series of requests to a stun server. A stun server is not something you need to set up on your own, because there are many free options out there from reliable sources like Google. Each peer will save their ICE candidates in the database, where they can then be read by the other peer. The algorithm will then automatically determine which candidate is best, at which point real-time media can begin flowing between the two peers. This has been WebRTC in 100 seconds. If you want to see more short videos like this, make sure to hit the like button, then stay tuned, because now we're going to build our own video chat app from scratch. That may sound pretty complicated, but the WebRTC API allows all this stuff to magically happen in the background. Over the next few minutes, you'll build a peer-to-peer video calling app from scratch using nothing but vanilla JavaScript and Fira as the signaling server. By the end of this tutorial, you'll know how to implement real-time features that cater to the needs of the new work-from-home paradigm that we live in. In addition to this video, you can also reference the full article on Fireship.io and the source code on GitHub. Let's start by taking a look at the demo. We have the local user's video feed on the left side and the remote video on the right side. The local user will first grant permission for the app to access the webcam. That user can then create a call, which will write a document to Firestore with the offer details. At the same time, we'll create a peer connection instance in the browser, which handles the WebRTC negotiation process. The offer will have a unique ID that can then be accessed by another user somewhere else in the world. That user will then join the call with the unique ID, then establish their own peer connection and write the answer details to the same document. Then both peers will write their ICE candidates to the database. We have one subcollection for offer candidates and another for answer candidates. This data model will allow signaling to take place between the two peers. The data itself looks like a bunch of nonsense, but what it contains is an IP address port pair that allows the two peers to establish a connection. Now both users can listen to this data in real time, then use the WebRTC API in the browser to establish the connection, giving us a one-to-one video chat feature. And now we're ready to jump into our JavaScript code. I started by creating a vanilla JavaScript project using a tool called Vite, which is a very simple build tool developed by the Vue.js guy. We can initialize a new project by running npm init vite.js/app from the command line. Basically, it gives us a web project where we can install dependencies without having to worry about things like Webpack. After initializing the project, we need to install Firebase. Firebase contains the Firestore database, which we can use as our back-end signaling server. Firebase is an exceptional choice for a signaling server because it's easy to listen to updates to the database in real time. If we were working with a traditional database, we'd likely have to implement something like WebSockets to make that possible. And this video would be a crazy 20 minutes long or something. From the Firebase console, initialize Firestore in test mode, then create a web project from the settings panel and grab your project credentials. We can then go into the main.js file, import Firebase, and initialize the app with our Firebase config. Now that we have Firebase set up, we're going to initialize 3 pieces of global state. These are values you would likely want to share between multiple components if you're using a UI framework like React or Angular. The first and most important value is the RTC peer connection. This object is where all of the action happens. It emits a bunch of different events that we can listen to update the database and to add media streams to the connection itself. One very important thing it does is generate the ICE candidates, but in order to do that, it needs to know which stun servers to use. There are many different options out there, but we're just going to use the free ones from Google. From there we have values for local stream and remote stream, which are the video streams from the webcams of each user. Now, because we're working with Vanilla.js, we need to use imperative DOM APIs. We're using document getElementById to grab a bunch of elements from the HTML, like video elements to show the actual video feeds, along with buttons that provide different interaction in the UI. The first thing the user will do is click a button to open up their webcam. We'll go ahead and register an event handler for the click event on the webcam button. Obtaining a stream from the user's webcam is very easy. We just await the Navigator Media Devices getUserMedia method, and we'll set video and audio to true. That'll bring up a dialog in the browser asking the user for permission to access the webcam. When that's complete, the promise will resolve to a media stream object. Once we have access to the webcam, we can also go ahead and set up the remote stream here, which itself will just be an empty media stream. Now from here, we need to take our two streams and make them available on the peer connection and show them on video elements in the DOM. The local stream is already running here in the browser, so we can get its tracks and then loop over them, and for each track, we'll call peer connection add track with that track and the local stream. Now the remote stream is currently empty and it will be updated by the peer connection itself. So what we can do is listen to the on-track event on the peer connection, then get the tracks from the stream, loop over them, and add them to the remote stream when they come in. Now the final step for managing our streams is to apply them to video elements in the DOM. We can do that by simply calling the video element source object and setting it equal to the stream. At this point, we have a way to manage a local and remote stream through the peer connection. But in order to make that happen, we need to do some signaling with Firestore. The user who starts a call is the one who makes an offer. We have a call button in the DOM to handle that functionality inside this async function here. We have a call document, which is used to manage the answer and offer from both users. Then we have offer candidates and answer candidates, which are sub-collections under that document that contain all of the candidates for each of those users. When we reference a document without an ID, Firebase will automatically generate a random ID for us. So we'll go ahead and use that to populate an input in the UI, which can then be used in another browser tab or by another user somewhere else in the world to answer the call. Now we're ready to create an offer and save it to the database. The first thing we'll do is await the peer connection create offer method, which will return us with an offer description. We'll then set it as the local description on the peer connection. Most importantly, this object contains an SDP value, which stands for Session Description Protocol. That's the value we want to save to the database, so we'll go ahead and convert it to a plain JavaScript object, then write it to the database by calling await call document set with that data. Now, what's inside the SDP object isn't really important, but it contains information about the video codec along with a bunch of other stuff to negotiate the connection. Now, one really important thing to point out here is that when we called setLocalDescription, it automatically started generating the ICE candidates. An ICE candidate contains a potential IP address and port pair that can be used to establish the actual peer-to-peer connection. We need to be listening to the ICE candidates, so it's important that we have a listener established before we make that call that listens to the onICE candidate event. When the event is fired, we'll make sure that a candidate exists, then write the data as JSON to the offer candidates collection. So at this point, as the caller making the offer, we are saving all of our data to the database. But now we need to also be listening for the answer from the user on the other end. The way we do that is by listening to changes to the call document in Firestore. The onSnapshot method will fire a callback anytime the document in the database changes. If our peer connection doesn't have a current remote description and the data has an answer, then we'll go ahead and set an answer description on our peer connection here locally. In other words, we're listening to our database for an answer, and when that answer is received, we update it on our peer connection. That negotiates the initial connection, but we also need to listen for ICE candidates from the answering user. We do that by listening to updates to the answer candidates collection. Firestore has a cool little feature where you can listen to only the documents that have been added to the collection, which is handled with the docChanges method on the query. So every time we have a new document added, we can then create a new ICE candidate with the document data, and then add that candidate to our peer connection. At this point, we're listening to updates from the answer side, but we still need to give the answering user a way to actually answer the call. Answering a call is very similar to initiating a call. The main difference is that we're going to listen to a document in Firestore with the same document ID that was created by the caller. We'll make a reference to that document as well as the answer candidates collection, then listen to the ICE candidate event on the peer connection to update the answer candidates collection whenever a new candidate is generated. From there, we can fetch the call document from the database and grab its data. It contains the offer data, which we can use to set a remote description on the peer connection. After that, we can then generate an answer locally, then set the local description as the answer. Now, just like we did with the offer in the previous function, we'll set it up as a plain object and then update it on the call document so that the other user can listen to the answer. In addition, we'll set up a listener on the offer candidates collection, and whenever a new ICE candidate is added to that collection, then we'll go ahead and create an ICE candidate here locally. And that's all it takes to build a video chat feature with WebRTC. The vast majority of the work is just signaling data between the two users. WebRTC handles all the complicated peer-to-peer networking and media streaming under the hood. I'm going to go ahead and wrap things up there. If this video helped you, please like and subscribe. And if you want to learn more advanced concepts about the web and Firebase, consider becoming a pro member at Fireship.io. Thanks for watching, and I will see you in the next one.